Hi there. A while ago I got this Chinese Demagnetiser or degausser. It is targeted to watch repairers, but of course it can be used for all kinds of demagnetizing jobs. I use it mainly to demagnetize tools like pliers and snips, and of course my clamp meter UT210E. And yes, I replaced the Euro-style 2-prong plug with a UK one. Let me show you how it works. I've got here a screwdriver that has been magnetized. As you can see, it can pick up that screw easily. When you press the red button, the unit generates a very powerful alternating magnetic field driven directly by mains AC power. To demagnetize an object, you keep it close to the unit and then pull it away smoothly while keeping the button pressed. Once you got the object at least 30 or 50 centimeters away, you can let go of the button. What the demagnetizer does when you press the button is to generate a powerful magnetic field that changes its north-south direction 50 or 60 times per second and a sinusoidal intensity variation. Any ferromagnetic object that you bring into this field is magnetized and follows along, doing the same changes in polarity and intensity. But that does not demagnetize the object by itself, far from it. As soon as you let go of the button, the field disappears and whatever object you try to demagnetize keeps the last magnetic orientation and field strength it has experienced. If you were lucky and turned it off when the AC voltage was close to zero, it might be demagnetized. But if you let go of the button at the peak of the voltage, it might end up being more magnetized than before. The trick to demagnetize with such a unit is not to only change the field orientation but also to reduce its strength. Since this cheap demagnetizer only changes field orientation, not strength, you have to do that yourself by gradually increasing the distance between object and demagnetizer. The magnetic field strength drops with the cube of the distance from the source. Moving the object slowly away while keeping the button pressed, the object is demagnetized less and less while constantly swapping north and south pole, leaving it with practically no residual magnetic field in the end. Inside this demagnetizer we find a transformer and a small PCB which connects the transformer to a push button and through that directly to mains voltage. There's also a red LED with a current limiting resistor in parallel to the transformer. The transformer has only a single coil and its core has been cut open. This means the magnetic field generated by the coil that would normally stay within the iron core now extends far into the space above the unit. The demagnetizer is being sold as for 220 volts or 110 volts, which means this transformer is probably a 110 volt type, which is seriously overloaded at 230 volts. This is really quite dangerous. The transformer survives when you limit it to just a few seconds of operation, with long pauses in between to cool down. I can tell you that with repeated use it gets very hot and starts smelling. Given that demagnetizing doesn't work unless you move the object away, I wonder how many folks unaware of this have pressed the button again and again, longer and longer, until the magic smoke and flames appear. Or put something heavy like a book or a tool on top and accidentally pressing the button while plugged in. To remove the need for sweeping hand movements and to make this device much more safe, I decided to modify my unit by adding a thermistor into the input. There are two types of thermistors, NTCs and PTCs. The latter stand for negative or positive temperature coefficient, which is way too long, so everybody refers to them by NTC or PTC. Now, the resistance of an NTC falls with rising temperature, so they are used for example in power supplies to limit the inrush current when you turn it on. The NTC, having initially a high resistance, starts letting in only a much reduced current flow. Yet it heats up because of that current and thereby reduces its resistance more and more, allowing the power supply to now draw its full operating current. PTCs work exactly the opposite way. Their resistance starts low and increases rapidly with raising temperature. This is exactly the behavior needed for fixing the demagnetizer. When I press the button initially, the PTC is cold, so it lets in a high current flow and the produced magnetic field is very strong. The current causes the PTC to heat up, and with that its resistance increases, throttling the current through the transformer and thereby the magnetic field. Since it can only go up to a finite resistance, there will always be a little current flow, so the magnetic field doesn't decay all the way to zero, but it's close enough. Long button presses or repeated presses in quick succession keep the PTC hot and therefore have no effect. You have to wait for it to cool down about half a minute or so before you have another go. Both are unpolarized and work with either AC or DC. Thermistors, apart from those high-ohm NTCs used as sensors, will significantly self-heat during operation. To pick the right PTC, we need to know what current the unit draws. An easy and safe way to find out is a power meter, which I built a while ago. I leave a link to the video in the description. The number we need is the current in the upper right of the screen. The unit draws around 210 milliamps when the button is pressed. That's 30 watts, no wonder it's getting so hot. I picked my thermistor from this datasheet from Vishay for the simple reason that almost all through-hole PTCs RS components offers are from this series. However, I'm sure the same principle applies to other brands. As a start, we want to make sure that this PTC is suitable for mains voltage application, which is true for this series, which is rated for up to 265 volts RMS or DC voltage. There are thermistors for automotive use which are not suitable for this modification. Next, let's look at this table. These PTCs are not linear, they act more like a fuse and have a distinct trip behavior determined by the INT max current, which is the maximum current when this thermistor won't trip yet, and IT min, which is the minimum current when it does. There's a gap where the behavior sort of transitions from the low ohm non-trip to the high ohm trip state. These currents depend also somewhat on the environment temperature and the mounting. In the case of the demagnetizing transformer, the normal power draw is 210 milliamps. That rules out all PTCs with an IT min current greater than that because they would simply not do anything. The second criteria is IOL, which is the maximum overload current. Since the transformer is drawing 210 milliamps, we can't use any PTC that can't handle this current, which rules out the first 4 of this list. We end up with just 5 candidates that would work in our application. To narrow the field further, we need to consider how fast we want the PTC to reduce the current when the button is pressed. For that, we need the overload ratio, which is the load 210 milliamps divided by the INT max current. For the first candidate, that would be 210 divided by 39, about 5.4. And for the last candidate, 210 divided by 110 or 1.9. We also note that the first candidate has a diameter of 5 mm and the last one of 7. With this data, we move to the graph of typical trip time as function of the current ratio. For the first candidate, we look up 5.4 and check against curve 7 for 5 mm diameter. It should trip within 1.5 seconds or so. For the last candidate, it's 1.9 against curve 6 for 7 mm, which looks like around 15 seconds, which would be far too long. The others are somewhere between these, but I think 1.5 seconds is a good value, hence I picked this one. Let's examine it more. Its cold resistance with 260 ohm is relatively high. I would have liked a slightly lower value, but the transformer is so much overdriven that the slight reduction in peak magnetic field should not matter. PTCs are not expensive, as you can see. Less than £1.20 for 5 if you take value-added tax or VAT into account. Of course, there's a shipping cost added to this unless you order more stuff from RS that gets you over the threshold. Since I got 5 of them, I decided to use one to run some tests and explore the world of PTCs, which I had very much neglected before. I started doing these tests with low volts DC as it's safer and much easier to control. First, I mounted my PTC in a fixture and added a temperature sensor so its tip was pressed against the PTC's body for good thermal contact. I measured the voltage across the PTC with a red meter, the current through it with a blue one, and the temperature with a yellow thermometer. The PTC was connected directly across one of my bench power supplies, and I simply increased the voltage in 1 volt steps. Because I needed to give the PTC time to settle temperature-wise, this test is very long, even at high speed, and it's hard to gather the behavior from the 3 instruments. So I decided to run this again, but automated, driven by my control program for the DPS5005 type power supply module that I showed in an earlier video, which I link in below. There's a slight change in instrumentation for that. The DPS5005 is recording voltage and current, but since the current has only 1 mA resolution, I decided to measure and record the current with my bench multimeter using its SCPI interface and use the red BM869 multimeter to measure the temperature, both controlled by the DPS5005 control program. Here you can see the power supply on the left and the bench meter on the right, both under remote control. The meter is taking a measurement every 2 seconds. A voltage change from 7 to 8 volts is just coming up. There. The slight changes in current shown by the meter after each step are because of the PTC warming up. On the bench, the PTC's instrumentation is unchanged, but the thermocouple is now measured by the red multimeter taking a sample every 2 seconds. Here you see part of the program listing that runs on the controller and the log output in the terminal window while it's being executed. Time to go for an extended tea break and let the software do the tedious part of measuring and collecting all data into one spreadsheet. The results are quite fascinating. First of all, these 2 graphs are really the same measurement. The left shows the current in red, while the right one shows the resistance as in volts divided by current. There was just no way of getting these 2 in the same graph with meaningful resolution. Anyway, the blue line shows the increase in voltage. We can see that the current increases, but at around 40 milliamps we now see these spikes, where the current first shoots up and then is dropping again as the PTC increases its resistance. You can see on the right that up to this point we had the expected 260 ohm resistance, even falling slightly with temperature, so our PTC was behaving a little bit like an NTC until that trip current was reached. As the current jumps up after each voltage increase, the PTC heats up more and increases the resistance, and that increase is more than would be needed to keep the current steady. It increases by so much that the current actually drops. This causes these spikes. Once a maximum of slightly above 45 milliamps is reached, the further increases in voltages cause so much increased resistance that the current now drops. It falls even well below the initial trip current, but of course the PTC is now very hot, above 80 degrees Celsius or so, it does not matter. It is interesting that despite reaching a thermal equilibrium, further increases in voltages causes an increase in resistance and a further drop in current. There's indeed more to the humble PTC than I assumed, but it's time to move on to test it with the actual demagnetizer and AC mains. You can see the prominent solder lugs of the push buttons sticking out from the PCB. These make perfect candidates to temporarily connect the PTC in series with the transformer using 2 test leads. This means, of course, that the button is out of action and the unit must be turned on and off with the usual switch on a UK-style power socket. As we are expecting trip times of less than 2 seconds, I connected my current transformer and used the scope for measuring the current. I made a video about this, which I link in below. The probe is set to the ×10 setting. We can see the expected behavior. A high current which starts dropping after around 1 second and decays quickly into a small residual current. The time base of the scope at 200 milliseconds per division shows that the drop starts before the 4th division and is well underway 800 milliseconds after the power was applied. Most of the drop happens in the next 400 milliseconds, and after that it settles into a very gradual reduction. This looks just as I hope it would look. Replacing the scope and current transformer with a multimeter, the peak current was 185 milliamps or so, which is because the 260 ohm cold resistance of the PTC in series with the transformer reduces the current. The long-time residual current is only 4 milliamps, not 0, but a reduction by almost 50 times. That should be good enough. Time to put this PTC permanently into the demagnetizer. But where should it go? On the transformer or on the mains side? And how to mount it? I tried this, desoldering one transformer lead and having the PTC take its place with the other end flapping in the breeze, as Dave Jones of the EEV blog would say. That works and is the easiest thing to do, but in the end I did not like it because the PTC does not affect the LED, so when doing repeated runs you can't tell from the light if the PTC has cooled enough for the demagnetizer to work again. So I removed the PTC and soldered the transformer lead back to where it originally was. I think the best way is to mount it here, between the push button terminal and the red mains lead, which means that thick track on the PCB needs to be cut. Another problem is the Chinese style strain relief knot. While it prevents the cable from being pulled out, nothing stops the cable from being pushed in and the knot hitting the newly installed PTC. That cable inlet has to move to the other side. The unit is now ready to get the PTC. You see, I made a fairly wide cut in the track to ensure that this gap is safely isolating the button from the mains input. And the mains cable is now coming in from the other side. The PTC is now in its place, reconnecting the red mains cable with the push button. I left the leads reasonably long and it's sticking out into the space vacated by the knot. This and the airflow through the gap of the previous mains inlet make sure the demagnetizer stays cool. How does it work? Here's a repeat of the test with the magnetized screwdriver at the beginning, but now with the modified demagnetizer. You can see the LED is going dimmer when the PTC kicks in. The flickering is a camera effect. Finally, I want to show what happens if you press the button too quickly in succession without giving the PTC and the transformer time to cool down. The LED clearly shows that the PTC isn't ready to allow the full demagnetizing effect, and this demonstrates why the more complex installation of the PTC at the mains side instead of the transformer side is worth doing. Thanks for watching.